We're going to move on now to a different method for analyzing trusses. We're going to look at something called the method of sections. This is kind of important for trusses, but the big thing is we're going to learn a method of analyzing structures where you make a cut and you look at what's happening to the structure internally. This will become clearer as we move on. First of all, why would we want to do this new method? Sometimes you only want to know the force in one member, and even though our shortcut is really fast, this could be faster. Although our shortcut's so fast, it might be faster than this method of sections. And you want to find this force in one member, and so you don't want to bother going through all the joints. What you want to do is just skip to the end and just solve for one joint. But how can we just skip to the end? Well, you need to turn into a truss ninja. And so if you've ever played this game, I think it's called Fruit Slice, you get a sword, and the object is to cut through all the fruit before they fall off the screen and not cut through any of the bombs. And so what we're going to want to do with this is slice through the truss. So you'll take your ninja sword and do that. Cut right through the truss. So what you do is, the first step is you slice through the member that you want to analyze. And so in this example, we're probably looking at one of these three members, and you slice through. I've been training you all semester to draw your free body diagram in these three steps, and this is why. We're going to apply it here. You're going to slice and draw a closed loop, starting with the ninja slice, and draw everything in the loop and only the things in the loop, and finally draw everything you cut with your ninja slice. And this is the method of sections. First of all, you have to solve for the reactions. There's no getting around that. That was problem 4 on the first test. Then you ninja slice, but the main thing is you can only slice through 3 members because each member will be an unknown and will only have 3 equations of equilibrium. You're going to close the loop after you slice 3 members and draw your free body diagram, and then you're going to use the equations of equilibrium to solve for what you're looking for. Here's a conceptual example coming up. In this example, let's say we wanted to know the force in member GC for some reason. And your first step is to take the slice. So a slice like this is no good because that's cutting through 4 members. Okay? A slice like that is no good. You look at it and you realize that this slice here, not a very straight slice, is the only slice that will cut only 3 members. Now the book gives it away. Usually they'll say things like, oh, find the force in members BC, GC, and GF. And they're basically telling you where to slice it. The hardest part in this problem usually is to determine a slice that only cuts 3 members. So this is getting a little confusing. Here in red, that's the slice. Now remember, you circle and close the loop. Well, you could circle this way and close it, or you could circle this way and close it. Either way would work. So if you circle to the left, the free body diagram would look like this, and if you circle to the right, the free body diagram would look like this. And remember, in step 1 you had already solved for these reactions. You could solve either this one for FGC, or you could solve this one for FGC. It's up to you. If it were up to me, I would circle to the left because this free body diagram looks less complicated than the one to the right. Let's do a numerical example. And in this problem, we're asked to find the force in this member HE. The first step is to find the reactions. I'm going to skip that for you. Here they are. This one here, sorry, is 7,500. The text box sort of made that go over to the next line. But there we go. The first step is to find the reactions. Now it's time to make the slice. And I've not told you 3 members to cut through. I said find the force in that one, HE. It's up to you to make a slice that will only cut 3. Well, it's pretty obvious that this right here is going to be the slice. Okay, now you can close either to the left or to the right. And what we're going to do is close to the right. Next, we're going to draw the free body diagram. And now that you look at it, you realize, oh, I didn't even have to find the reactions first. If I just sliced it and circled to the right, I could solve it without knowing the reactions because they're outside of that loop. This is why I've been teaching you how to draw the free body diagrams this way. Okay, looking only in a loop, let's draw everything in a loop. So we have that, this little triangle here, that member, and there. Now I'll draw everything in the loop and only what's in the loop. The only loads in the loop are this 1500 and that 1500. And finally, draw the forces that we've cut through, or everything we've cut through. We've cut through this member up here. That's FGH. We've cut through that member there. That's the one we want to know. FHE. And we've cut through this member on the bottom. FED. Okay. And now what we want to do, now that we have the free body diagram, is use our equations of equilibrium to solve for the force. Oh, by the way, I drew all those forces pulling away from the members. I drew them all in tension. So if I get a negative, that means it's in compression. Well, if you wanted to find FED, which we don't, you would take moments about here, where these lines meet. If you wanted to find the force in FGH, which we don't, you would take moments about here, and then you could solve for FGH. But we want to know FHE, and I can see that if I take some forces in the y direction, I'll be able to solve for FHE. Let's call that theta. FHE sine theta going up, positive, minus 1500 minus 1500 equals 0. FHE equals 3000 divided by sine theta. Let me go look at the picture and figure out what theta is. The angle theta, I was looking at the picture. It's nice. It's a 3, 4, 5 triangle like we've always been using. So that's theta. And sine theta then is 4/5 or 0.8. And FHE then is 3000 over 0.8, which is 3,750, and these were pounds, or 3.75 kilopounds or 1,000 pounds, and we call those kips for kilo pounds. I know it's kind of weird, kips, but again, it's kilo, pounds, or kip.